I introduce our third keynote speaker for today, Professor Ratnajit Bhattacharya sir. Sir is a very eminent professor at Indian Institute of Technology, Guwahati, from Department of Electrical and Electronics Engineering background. Sir is presently heading the Mehta School of Artificial Intelligence at IIT Guwahati. And today Sir will deliver the fundamentals of the optimization techniques, the classical optimization techniques to you. Over to you and welcome, sir.
Thank you very much. Thanks for Nandaji for inviting me. And I could see a host of modern optimization techniques are being discussed. And what I'm going to discuss is based on some classical optimization, which essentially we teach at the undergraduate data science program. And so the discussion will be on how the mathematical background, whatever we expect, and because algorithmic based, ultimately, be it GA, PSO, everything finally wants to find some maximum or minimum. And classical optimization started as solving a mathematical problem. So I take this opportunity to interact with you. Can I share my screen? And
Yes, sir. Please share your
Okay.
screen, sir.
Okay. Just give me 1 second. So I'm stopping my video for conserving bandwidth.
Sir, bandwidth is not a problem for us also. You can keep your
No,
video.
not for you, but at my end.
Sir. Sir. Okay.
So is my screen visible now?
Yes, sir. Visible, sir. Sir, if possible, make it full screen.
Yeah, I'm going to full screen only. Just trying to use that window.
Yes, sir.
It is visible now?
Yes, sir. It is visible, sir. Completely okay, sir. Sir, just change to next slide. One slide. Yes, sir. It is perfectly fine, sir.
Thank you. Thank you for this feedback.
Sir.
And I am audible properly?
Yes, sir. Perfectly audible, sir. And slides are perfectly changing.
So as I have been requested to talk something on the classical optimization technique, I actually pulled up some of the slides from the content that I usually teach, and which I teach over a semester, as you can understand. So it will not be possible to touch upon each and every topic. I will give a summary of this and focus on 1 or 2 topics. So this is slides are based on a reference book, Chong and Zhak, An Introduction to Optimization, 4th edition. This is a very, very standard international text, and we follow this. So what is optimization ultimately? It is the process of finding the best solution to a problem, and from a set of possible choices, usually by maximizing or minimizing an objective function. So an optimization may be maximization of a problem, or it may be minimization also, while satisfying certain constraints. The solution should satisfy certain constraints. So mathematically speaking, if you put it like this, it is mean of fx or max of fx, where fx is an objective function to be optimized. And x represents the decision variables. We will use a vector here, and S is the set of feasible set defined by the constraints. So this is in short an optimization problem. And as you know, the application everywhere, everything we do, even every day-to-day life also, we look for optimization, minimizing something, maximizing certain things. So in the engineering and design optimization, cryptography, security, they use optimization to balance the security and efficiency. Machine learning, data science, they use gradient-based optimization to minimize loss functions. Operation research, logistic, economics, finance, physics, computational science. So the area is endless. In fact, everywhere it is used, and although the fundamental principles are more or less same, the problem is presented considering the context on which it is being applied. Nandaji, at times I will probe you whether you can hear me and see my slides. I hope my slides are visible and I am audible.
Sir, you are audible.
Thank you, thank you. Please kindly respond any of the participants also, because I could see a large number of participants joining this program.
Sir, this is Dr. Nanda, sir.
Uh-huh.
Sir, actually, here participants will interact with you only in the form of chat. They will not be allowed to speak on this particular platform, sir. On muting and speaking, we have little bit restricted because of 400 plus number of participants.
I understand it becomes a chaos. So if some of the pertinent questions, maybe time to time, if you can relay me.
Yes, sir. We will relate to you, sir.
Yeah, just tell me that this is the questions and then I will try to answer. Huh?
Sure, sir. That we will do.
Because if I give my attention to the chat box, then
no, sir. You do not have to give anything to your chat box. You just complete the lecture. Then all the important questions we will be passing it to you, sir.
So
sir.
I hope that because I will require a little bit of mathematical background, everybody having backgrounds on some linear algebra, calculus, and all these things, because it is a classical optimization methodology. Anyway, that you will get to see how we will form the problem. So modeling and solving optimization problems, we start from real life problem, we pick up. Then we do a modeling to have a mathematical formulation of the problem. Then we usually apply any optimization algorithm. We get a set of solutions, and from this set of solutions, we choose the optimal one. And this goes on. So this is modeling and solving optimization problem, and the reference I have mentioned below. So let us take a very simple one. Since we are talking of classical optimization problems, let us take a very simple one. How we formulate the problem. Suppose our objective is to find a rectangle with the largest area among the rectangles with a given perimeter L. This is a very simple problem, usually taught in school level also, but just to show how systematically we can formulate the problem, I have picked up this example. So we have a constraint on the perimeter L, and our objective is to find we know the shape, rectangle, and find the area of a rectangle which is maximum. So here our decision variables are the lengths x1 and the width x2 of the rectangle. We can play with these decision variables, but we have a constant of L, so that means we'll have to choose x1 and x2 in such a way that this perimeter L constant is satisfied. Since we are looking for a rectangle with maximum area, the objective function, which is a function of this x1 and x2, it is x1 into x2, that will give us the area. And the constraint is 2x1 plus x2, 2 times the sum of the length and width, which is the parameter, is L. So given this formulation, now we can write our problem in a formal mathematical form. Max x1, x2 belonging to R is a set of real numbers, and f of x1, x2 subject to 2x1 plus x2 is equal to L, and we must also have, we cannot have x1, x2 negative, so x1, x2 greater than equal to 0. And of course, any one of them becoming 0 also will make it a line anyway. So this is the formal mathematical statement we formulate to solve a simple optimization problem. Now, how do we solve it? That we will discuss. I'm just discussing how we put our observation in the form of optimization problems. I pick up another simple example, slightly difficult and more practical. Suppose we have a company that manufactures 4 products requiring time on 2 machines and engages 2 types of workers, skilled and unskilled. And their engagement is shown here. Suppose it 4 products, 1, 2, 3, 4, and machine time on different products for the machine 1 is given here. Machine time on machine 2 for different products is given here. And hours of skilled worker that we want to spend on a machine is given. Hours of unskilled worker, I think this is, one should be unskilled, sorry for the mistake. And the unit sell price is given. So this table is given to us. Now, as a company, we want to manufacture some number of the products so that we get best of the profit definitely. And we also have to satisfy the constraints. Suppose each month 600 hours are available on machine 1, that means we cannot exceed this, 500 hours of machine 2, and each month the company can purchase up to 700 hours of skilled labor at the rate of 200 per hour, and up to 650 hours of unskilled labor at the rate of 100 hours per hour. So given these values, 600 hours, 500 hours of machine time on 1 and 2, and 700 hours of skilled labor, 200 hours, rupees 200 per hour, and 650 hours of unskilled labor at 100 per hour. Now the company wants to determine how much of each of the product it should produce each month and how much labor to purchase in order to maximize this profit. And profit we define revenue from sales minus labor costs. So we put it in a formal mathematical setting. Let xi, I belong to 1, 2, 3, 4, represent a number of units of the ith machine to be produced. Ys and us are the skilled and unskilled manpower to be purchased. And we are assuming that whatever we produce, everything is sold, so that we do not have any leftover. To simplify the problem, then the company cost will be 8,000. Company profit will be 8,000 x1 sold, 6,500 into x2, 6,000 into x3, and 4,000 into x4. So these figures, they give the selling price minus 200 ys that we have actually bought, and 100 yu. So these hours are unknown to us. These numbers x1, x2, x3, x4 are unknown to us. And then constraint on machine times, we have 12 x1 plus 8 x2 plus 6 x3 plus 6 x4 less than 600. Because this is the time you need to spend on product 1, this is product 2, like that. And for the other machine, we have this set of constraints again, similar. Now, given this, all this information put together, and skilled manpower, we have this constraint because we had some figure how much a skilled manpower will spend on product 1, product 2, like that. Similarly, how much manpower would be required for product 1, 2 for the unskilled. So all this information, if you put it together, we now get a optimization problem to be solved. Maximize 8,000 x1 plus 6,500 x2 plus 6,000 x3 plus 4,000 x4. So that is you earn by selling your goods minus 200 ys plus 100 yu, that is what you spend on manpower. And then subject to these constraints, first two constraints are on the machine time, second two constraints are on the manpower you purchase, and then ys has to be less than 700, yu has to be less than 650, and all these 6 unknown variables x1, x2, x3, x4, ys, yu must be greater than equal to 0. So this problem, when you solve to get the maximum value of this, so it becomes an optimization problem. And as many of you who are familiar with optimization have understood, it is a linear programming problem. And even today, we have the solvers in Excel which can easily solve this type of problem. Am I audible, please?
Yes, sir.
Thank you. So I initially made a plan of presentation to cover the entire domain of classical optimization. I have noted down the topics which we normally discuss, but given on the constraints on time that I have, I will confine my discussion on a very popular method of optimization, the gradient method, and the method of steepest descent. Other, I will make cursory mention. For example, an improvement of this gradient method, we find Newton's method, and then we get Levenberg-Marquardt modification. Then there are quasi-Newton methods, and linear programming is something what I have just discussed. Many problems can be posed as a linear programming problem. Please note that we are calling it linear because the cost function is a linear combination of the decision variables. And then we have a very elegant way of solving linear programming problems. It is the simplex method. And then linear programming problems can be posed as dual problems. And then we have nonlinear optimization problem, the constrained one with equality constraint. And a very popular method of solution of nonlinear optimization problem with equality constraint is Lagrange's condition. The very first problem we discussed, our objective function is a product of two decision variable x1, x2, and their sum, the constraint, is equal to L, so it's a equality constraint. So these are small examples I am citing to give you an idea about how we distinguish among different varieties of these optimization techniques. And then there are problem with inequality constraints and Karush-Tucker condition, very popularly known as KKT conditions. These are applied. So the domain of classical optimization is also very vast. Although nowadays the optimization either goes towards genetic and colony, this type of algorithmic based optimization problem. These problems, optimization techniques, what I'm discussing, these are also very powerful in solving many of the engineering problems, and in fact has very strong mathematical basis for whatever you do. So I will start with this. I'll try to cover in today's this discussion very basics of set constraint and unconstrained optimization. Condition for local minimizer, we call FONC first order necessary condition, SONC second order necessary condition, and SOSC, so second order sufficient condition, based on which you can tell whether you have solved an optimization problem or not. And gradient methods, these are very much in use even in data science and AI. The gradient methods are very popular. So I will just touch upon these few topics given the constraint of time, and we'll try to see little bit in detail. Make sense, sir? Nanda, sir?
Yes, sir. Sir, please go ahead, sir.
So first of all, we'll deal with a n-dimensional vector space Rn of real vectors, and suppose a vector D belongs to Rn and D is not equal to 0. It is called a feasible direction at x belonging to some space omega, if there exists some alpha which is greater than 0, such that x plus a alpha d belongs to omega for all alpha within the interval 0 to alpha naught. So it is feasible direction is important because for an optimization problem within the constraint set omega, a minimizer may lie either in the interior region or on the boundary of omega. So we have seen x1, x2. So this is a 2D space. Similarly, as your number of variables will increase, you will have higher dimensional spaces. And a vector D it is called a feasible direction if it follows this property. Another notation we'll use, for example, argmin fx, which denotes the argument that minimizes the function f, assuming that such a point is unique. For example, if I take a simple function, one-dimensional case, a function from R to R, not from Rn to R, then f of x given by x plus 2 square plus 2, argmin fx is minus 2, because this is the only value which will give you the minimum of the function. You take any other value, positive or negative, because it is square, so this is going to be positive and greater than 2. So this argument, this notation we'll use to denote, and here our function f is a function of a vector x. I hope it makes sense. So unconstrained optimization refers to finding minimum or maximum of a function when there is no constraint on restriction on the input or the decision variables. That means x. X is a vector here, and we have the components x1, x2, x3, xn, like that. And we can search for all local extreme values and compare values of function at each of these to find the global optimization point. And constraint optimization, on the other hand, requires decision variable to satisfy certain constraints, and the constraints may be equality constraints or inequality constraint. In some cases, it will be exactly equal to the constraint. In some cases, as you have seen, we said that the vector x has to be greater than equal to 0. So these are inequality constraints. So let us put a optimization problem in the standard minimization problem. Why we always talk about minimization problem? Because if we can find out minimizer for f of x, and maximizer is essentially that of negative minus of f of x. So the same procedure applies. So we have a function f of a vector x, and subject to x belonging to some set omega, and f is a function from Rn to R, n-dimensional space, to a set of real numbers, is the objective or the cost function. And x given by a vector x1, x2, xn transpose, it belongs to Rn. And x1, x2, xn, these are called the decision variables. And omega is a subset of Rn, is called the constraint set or the feasible set. So this is the way a standard minimization problem is represented. So if you choose omega equal to Rn, the problem is unconstrained optimization, and the constraint x belonging to omega is a set constraint. There may be other form of constraints which are called functional constraints, like x satisfying h of x equal to 0, g of x less than equal to 0, and h and g are given functions. So our optimization problems usually are posed in this language. We talk of local and global minimizer, uh, like your PSO, then your GA or and colony, this type of optimization algorithms, they always say that it can always give you the, if you have multiple maxima and minima, then you can go for the global minimizer. You use if it is stuck in a local minima, so from there it comes out and finally reach the global values. So for f Rn to R, a real valued function, and x star belonging to omega, local minimizer means if there exists a omega greater than 0 such that fx is greater than or equal to f x star for all x belonging to omega but not equal to x star. And here you define a small region surrounding x star where f of x star is the minimum value. And a point x star is a global minimizer if for all values of x, f of x star is the minimum. And for strict local minimizer, greater than equal to is replaced by greater than sign. So whatever I told, if you try to visualize it pictorially, so we have a strict global minimizer here because there are multiple minimizer, but this minima is the lowest one. This is also a strict local minimizer, but not a global minimizer. And this is a Plato type function where it is a local minimizer, but it is not a strict local minimizer. So the first order necessary condition says that if a function f is differentiable form, then the following condition is satisfied. T transpose D is the feasible direction. Gradient of fx star is greater than equal to 0. So this is the general condition, and if x star is an interior point on omega, then f1c reduces to gradient of fx star is equal to 0. So gradient finds a lot of application in classical optimization because gradient is the rate of change. And the rate of change of a function at a particular point, and also it is a vector, and the direction of the gradient is where this rate of change is maximum. So if we are searching for a minimum, we should try to move towards the direction negative of the gradient that we will discuss when we state the gradient based optimization case. A few more definition, because many a times if your objective function is a convex function, then it is easier to find a solution because in this case your local minima becomes the global minima. And how we mathematically define? We define a line segment between 2 points x and y in Rn. So z is a point on the line if it satisfies this condition that alpha x, z equal to alpha x plus 1 minus alpha y, and alpha belonging to the interval 0 to 1. Now 2 points u and v are line segment we have already defined. A point is called a convex combination of the points u and v. And a set theta being a subset of Rn is convex if for all u and v belonging to theta, the line segment between u and v are in theta. So this is convex set, and the examples of convex set here, if you take any u and v, the line joining them lie within this. Similarly, if you take a regular hexagon, it is a convex set. But these are non-convex example of non-convex sets. U, V, the entire portion of the line does not lie within this figure, and also not for the second figure. So now we define a convex function, a function f from omega to r defined on a convex set omega, which is a subset of subspace or subset of Rn, is convex if and only if for all xy, which is should be belong to omega, sorry for the typo, and alpha belonging to omega 1 0 1, we have f of ax plus 1 minus alpha y is less than equal to alpha fx plus 1 minus alpha y. So this is what is shown here as a geometrical interpretation. So here you can see this line, it is always lying above the curve. So not going into much of the details, a graph of a strictly concave function always lies above the line segment connecting any 2 points on the graph. And for a convex one, the graph lies below the line. So a geometrical interpretation, a line joining any 2 points on the graph of the function stays above the graph. So this line and the graph remains below. So we come to the second order necessary condition. So if x star is a local minimizer of f over omega, and for any feasible direction d at x star, d transpose gradient of x star is equal to 0. So that condition is satisfied. And then we have d transpose f. F is the Hessian of f, function f, dt, if it is greater than 0. Then for all d belonging to omega, d transpose fd greater than equal to 0. So this is the most general definition. A simplified one is x is an interior point, then x is a local minimizer if gradient of f is equal to 0 and Hessian x star is positive definite. And this positive definiteness of the Hessian matrix is denoted by this. I'll explain all these things with some examples. So second order sufficient condition, if x be a function which is twice continuously differentiable, and if we have gradient of fx is equal to 0, then for all d belonging to Rn less than this 0, dt del square fx d greater than 0, then it is a strict local minimizer of f. And alternately, we can state that gradient of fx star is 0 and Hessian of Hessian capital F x star is greater than equal to 0. So these conditions are used. For example, if you take a one-dimensional case, the first thing we do, we find dy by dx and equate it to 0. And then we find out second derivative, d square y by dx square. And based on the sign of it, whether it is greater than 0 or less than 0, we declare a maxima or minima. And these definitions are actually a generalization when you have multiple objective functions, multiple decision variables. So this is the case. A simple example is shown. Suppose f is a function of x1 and x2, and it is given by f of x is x1 square plus x2 square. So this can be stated as f of r2 minus r2 to r, and gradient of fx here, you can find out 2x1, 2x2 transpose. And if you find out the Hessian, then it is a matrix 2, 0, 0, 2. Therefore, x star 0, 0 transpose satisfies gradient of x is equal to 0, and the eigenvalues of del square fx are greater than 0. So it is a positive definite. It is positive definite, and therefore satisfies SOSC. And therefore x star is a strict local minimizer of f. And if you plot this x1 fx as a function of x1 and x2, we can visualize it till it is function of two variables, because we can plot it as a 3D. But if you have more variables involved, then you will have to go by the mathematical statement only. So here you get at x is equal to 0, y equal to 0, x1 equal to 0, x2 equal to 0, our function f is having a minimum value. And it is quite obvious from the statement also. For any other x1, x2, positive or negative, this will have a non-zero value. And here you can also see that we have this function. It is actually, if you draw any line, so that line will lie above this, and therefore will give you a convex function, and it has a unique minima. So these are simple examples I am drawing to explain the concepts which are used in classical optimization in much more difficult, solving much more difficult programs. Here you see another example. By the way, these plots are made with MATLAB, so indirectly we are engaging MATLAB also. So if you have x1, function of x1, x2 given by this, then you get the gradient of f, and gradient of f to become 0 requires x1 to lie in the range -2 to 2, x2 -4 to 2. And these solutions you will get, sorry, it is not in the range. x1 has two solutions, -2 and 2, and x2 -4, 2 within this set. And therefore, if you find out f of x, the Hessian, it is 2x1 2x2. Now, strict local minimizer will be x naught is equal to 2, 4, for which this will be positive definite. And strict local maximizer will be -2, -4, this combination, because it will be giving you a negative definite. And for other combinations, you will not get maxima or minima in the strict sense. So this is how we utilize these conditions: FONC, first order necessary condition, SONC, and SOSC is the confirmation second order sufficient condition, to determine whether a particular point represented by a vector x, it gives the maximum or minimum value of a function f. Let me now go to gradient based method, because gradient based methods, these are very popular, as I mentioned. And here we consider a class of search method on real valued functions on Rn. And these methods use the gradient of the given function. So a level set of a function is a set of points x satisfying f of x is equal to c for some constant c. So these are shown. And a point x naught belonging to Rn is on the level set corresponding to level c if f of x naught equal to c. So this is x naught, and this is the level set, and this is z is equal to f1, f of x1, x2 is the function, and z is equal to c. It intersects this along this, and this is projected here. So the gradient of f at x is equal to 0, if it is a non-zero vector, is orthogonal to the tangent vector to an arbitrary smooth curve passing through x naught on the level set fx is equal to c. And direction of gradient of x points in the direction of maximum rate of increase of f at x. And therefore, negative of fx points in the direction of maximum rate of decrease of f at x. And therefore, the direction of negative gradient is a good direction to search if we want to find a function minimizer. Now, there are a class of search algorithms which are also used, because ultimately you can use one-dimensional search algorithms like your bisection algorithm or second methods and all these things to locate the minima, to find the route where in each of the directions you use. So it is a search, but search on a space represented by a function of multiple variables. So gradient descent algorithm, it says let x naught be the initial point. We consider the point x naught minus some alpha into gradient of f at x naught, and then use Taylor's theorem, and then if gradient of fx naught is not equal to 0 for sufficiently small alpha, then f of x naught minus alpha gradient of fx naught is less than f of fx naught. And therefore, this quantity x naught minus alpha gradient of fx naught is an improvement. It is an improvement over x naught in the search for a minimizer. So we can put it in iterative form. In order to implement the idea as an iterative algorithm, if xk is the given point, we find the next point xk plus 1 as xk minus some alpha k gradient of f of xk, where alpha is the step size and the algorithm is referred to gradient descent or simply gradient algorithm. And this is very popularly used. The gradient varies as the search proceeds and tending to 0 as we approach the minimizer. So this is the basic idea. Iteratively, we go towards the slope of the curve. Finally, we reach a point where the gradient becomes 0. And there we locate a minimizer. Now, gradient descent itself is an algorithm, optimization algorithm. Method of steepest descent, it goes one step further. In this method, the step side alpha k is chosen to achieve the maximum amount of decrease in the objective function in the individual step. So in other words, we use alpha k argmin. Now we make use of the symbol what we introduced, f of xk minus alpha gradient of f of xk. So we find out a alpha k which minimizes this. And at each step, starting from a point xk, we conduct a line search. That's what I mentioned, that in the direction of negative of gradient, we try to find a line search, and there are several line search algorithms, one-dimensional line search algorithms are available until a minimizer xk plus 1 is found. So this is depicted here. So we start from x1, x0, we go to x1, from x1 to x2. Like that, we keep on progressing on the level sets. And then finally, we reach the minimizer point x star. So if the objective function can be written in the quadratic form, that means if we can write f of x as half x transpose qx minus b transpose x, and q belonging to R n cross n is a symmetric positive definite matrix, then the algorithm can be modified like this. Now, how we can put a function in a quadratic form? So this is shown with an example. For example, here f of x1, x2, it is expressed in the quadratic form, and we have the vector x is x1, x2, q is here 2, 0, 0, 2. So it is a symmetric positive definite matrix, and minus the vector 8, 6 into transpose into x1, x2. So in that way, you can formulate the problem, and I've not gone into the derivation of if you can formulate it problem in the quadratic form, then also you can find out xk plus 1. And if you are using steepest descent method, within few steps, you will converge to the minima. Now, any optimization problem, we look for many things: the speed of convergence or rate of convergence, and finally whether we could achieve the desired amount of accuracy in finding the minimum point. And also, since this type of things will be finally implemented using some computational algorithm, the computational complexity is also an issue. Next, modification of steepest descent, because this descent algorithm, they use only the slope, the gradient. So Newton's method, it uses the second order del square function also, and it tries to approximate the function with a second order function. So those modifications are done, and then it brings in some computational complexity, and inverse of metrics need to be computed, and therefore the classical optimization techniques also keeps or goes on finding out better and better solution which can give you faster convergence, which are very accurate and computationally less demanding. I think I have already reached almost the end of my allotted time, and thanks for your attention. I'm ready to take up some of the queries if you have posted any.
Thank you, Ratnajit sir, for giving us very fundamental to the gradient-based methods and Newton methods. Sir, I request all the participants to put the questions in the chat box.
Nanda, sir, can you please unshare me, because then I can
Yes, sir.
then I can turn on my video and we can go on the discussion mode.
Sir, you can on-share it.
Yeah, somehow my screen. Okay, there. Stop sharing.
Stop sharing, sir.
Yeah. Rajesh ji puts hand. I think he has some query. I could see on. Okay, how to decide which method? This comes from the experience. That's why which method is suitable for a particular optimization problem, it depends upon the nature of your objective function also. If your objective function is a linear objective function, then people usually go for linear programming, because you have very elaborate and robust tools available for solving such. You need to only formulate it properly, and as I mentioned, even the Excel has a solver. Whereas if you have the objective functions which are nonlinear functions and all, in that case you can think of optimizing using the other methods which I have mentioned. In fact, many of these algorithms what are going to be discussed in this course, many people use them, but my request is, whenever you use any algorithm, you just do not use it as a tool. It is important to understand the mathematical basis so that you do not misinterpret or you do not miss the solution or get some solutions which are not actually the solution. So it comes with some experience, how the problem, in what way, and usually people go by the strength, their strength. If somebody is uh, strong in formulating problem as a classical optimization problem, they will try to do so. If somebody has strength in evolutionary type of algorithm, they formulate it. So there is no unique answer for that. It is guided by the nature of the problem. It is guided by the expertise of the person solving the problem. But optimization is very, very important, every sphere. And engineering problems means finally you have to optimize performance, improve it. Sir, can we close the session now?
Sir,
Or
just
there-
1 minute. Few couple of questions put by the scholars. One is that how to calculate the complexity of the algorithms.
Yes. So complexity analysis, convergence analysis, these are very, very part of comparing the performance of optimization algorithm. And in fact, because of this only, there are so many algorithms. I have given, if you are talking about the classical optimization technique, a very thorough analysis of the convergence issues and these things have been done in the reference I have mentioned. I do not know how many of you follow this book, although it is written Introduction to Optimization, but the Chong and Jack's book is really very good. It covers all the theoretical aspects to a great detail.
Sir, another scholar is asking about the initial values, how to decide the initial values of the algorithm when we are processing the thing, proceeding with the thing.
Yeah, so it can be shown, it again depends upon the nature of the problem. For example, if a function is a quadratic function, it can be shown that in a classical optimization setting, it does not really depend on the initial value much. It converges in the very next step itself. But some of the problem, if it is not a quadratic function, then it will take several steps. And if you are closer to the minima or maxima, that actually become very helpful for better convergence. I do not have a straight cut solution for answer for this.
Sir. No. So, thank you, sir, for giving enlightening us with the very fundamental about the classification algorithms. I think it is a very fruitful session for all the participants who have joined throughout the country. I am thankful to Ratnajit Bhattacharya, sir, for answering all the queries of the participants. Sir, also, I request you to share the slides after it so that we will share it with the participants.
Okay. I while delivering this talk, I noticed 2-3 typos there.
Sir,
I'll get it corrected and then mail it to you.
sir.
Okay.
Thank you, sir.
Thank you. Thank you. I wish it will be a great. It is a joint initiative of all the E and ICT academies.
Yes, sir. It is a joint initiative, sir.
So now I, of course, but IIT Guwahati EICT Academy was founded by me only.
Yes, sir.
I was the PI. Of
Yes.
course, now my colleague Dr. Gaurav is looking after. Yeah. So whenever there is a call from any of the E and ICT academies, I consider it to be a responsibility to respond.
Right.
Thank you very much for inviting me. And if the participants have got benefited because of this discussion, it will be my pleasure.
Sir.
Wish all of you good night. Thank you.
Thank you, sir.
कैनवास ज्वाइन के लिए कैनवास ज्वाइन के लिए भी अटेंडेंस को
So I request all the attendees to join the Canvas link. On the Canvas link, we will share all the materials. Also, today's recorded videos we will be sharing over the YouTube link to all of you, so that those who have not gone through the past two sessions, they can also look at that particular one. And the most important thing is your attendance. We are recording them in the WebEx platform. So all the participants have to join the WebEx platform to get the certificate and the attendance recorded. So that is what from our side for today. So thank you all.